This exercise and the next exercise are about using the Hilbert matrix to explore the numerical inaccuracies that come from trying to compute the explicit inverse of a matrix. This is one illustration of why, in practice, in applied linear algebra, you try to avoid explicitly inverting a matrix when possible, because even theoretically invertible matrices might be difficult to invert in practice. So the goal of this exercise, exercise 9, is to write a Python function that will implement an equation that I'll show you in a moment to compute a Hilbert matrix and then reproduce a figure. And I'll show you, we'll work with the inverse of that matrix in the next slide. So we're going to start by implementing the formula as directly as possible. And then after you've implemented that formula, you can adjust the code to make it a little more compact, a little bit more efficient by using the outer product instead of a double for loop. Okay, so let me show you the equation. Here is the equation for generating a Hilbert matrix. So Hilbert matrix H, and this refers to the definition of matrix element I comma j. So I comma j, it's very simple. It's 1 divided by I plus j minus 1. Now, you have to keep in mind that mathematics, like chalkboard mathematics on a piece of paper or on a chalkboard, is indexed using 1. So it's 1-based indices, which means that the first element, so element 1 comma 1, which means the first row and the first column, is actually I equals 1 and j equals 1. But Python, as you know, is a 0-based indexing language. So that means the index or the element at row 0, column 0, actually has to be adjusted appropriately so that these indices reflect 1-based counting, although the Python coding needs to be 0-based indexing. It's even confusing just to talk about this, but I think you get what I mean. This confusion comes up pretty often in coding, in particular in coding mathematics and applied mathematics. So that is one of the important take-home messages from this exercise, is always to be careful with indexing in mathematics versus in Python coding. Once you have written a Python function to implement that formula, then you want to create this figure where we see the Hilbert matrix for a 5x5 Hilbert matrix, its inverse, and their product. And of course, this should be the identity matrix if this really is the inverse. Here is the Python function that I wrote to create a Hilbert matrix. You can see I start by initializing a matrix of zeros, and it's going to be a k by k matrix for some integer input k. Here I have the double for loop, and I'm using a double for loop here because I want to implement the formula as it was written in the book, in the equation there. Now, this initially might look wrong because the formula is actually 1 divided by I plus j minus 1, whereas here I have I plus j plus 1. So that initially seems wrong, but like I said, there's this confusion that comes with the indexing. So really, you need to say I plus 1 plus j plus 1 minus 1. But then it turns out with all these extra ones here, right, you have 2 additional plus 1s and a minus 1, so that boils down to plus 1. Okay, so this is fine, but then here I show a different way to implement it, where I say a range of numbers, so I get a vector that goes from 1 to k. Of course, we have to write k plus 1 because these are exclusive upper bounds. So all this stuff gets really confusing, especially if you are new to Python or if you are new to Python from another language that is 1-based, like MATLAB or Julia. Anyway, so here I define a row vector, and then I transpose that into a column vector. And here I'm just using the outer product to implement exactly the same result here. So we still have this matrix H being returned here, but this is, but we don't need any for loops here. Okay, so I'll run this. And then let's see. So here I'm just going to print out this result here. Here you see the Hilbert matrix. Now you're used to seeing this as fractions. So this is 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 4, and so on. It turns out, I really wanted you to do all of this stuff by hand just to help you appreciate the annoying difficulties of translating math with 1 based indexing into Python with 0 based indexing. But there is a function in scipy.linalg called Hilbert, and that's, of course, in practice, that is much easier to use. Okay, so then, without really worrying too much about the numerical stability of the inverse of the Hilbert matrix, I'm just going to compute the inverse and make some plots, and that you see here. So here is the visualization of the Hilbert matrix, its inverse, and their product. Now, one thing you can already see is that the numerical values of the Hilbert matrix are between 0 and 1, but the numerical values of the inverse of the Hilbert matrix are huge. Look at this. It goes from minus 100,000 up to over 150,000. So the numerical range of the values here is way different than in the original Hilbert matrix. That is already a clue. It's already an indication that this is not a numerically stable operation.